Surely you can't be serious.
I am serious. And don't call me Shirley.
The laws of inference are basically arguments that show up over and over and over again in math, so much so that they get special names. So the first question is, what exactly is an argument? Well, an argument is basically the process of using statements which are known to be true to justify the truth value of some new statement. Those statements which we already know to be true, statements with given truth values, called the premise of the argument. And the statement that we're trying to show to be true, the justified response to the premise, is called the conclusion. So every argument is made up of a premise, which is given information that we already know to be true, and we're trying to arrive at some new statement or to justify an extra statement, which is the conclusion, which is the response to the premise. So here's an example of a basic argument. Now, the first two pieces of this argument, denoted with a capital P1 and a capital P2, is basically the premise of this argument, and the portion denoted with the C is the conclusion of this argument. This is a special argument. It's actually one of our laws of inference. It's called the Law of Detachment. And the question is, well, how do we know that this conclusion is a justified response to the premise? Well, we have to justify it to ourselves. So first I'm going to do this informally, using this truth table to my right, and then I'm going to show you how to formally justify an argument, which is a little bit more of a rigorous process. So first off, whenever I set up a truth table, I have two basic statements that I'm testing here, P and Q. So I'm going to fill in my truth values, every possible pairing of those truth values, true with true, false with true, or both false. And then I'm going to use my broken promise rule to determine when this conditional statement will be false. Well, it's false only in the true to false situation, which is here, and will be true in all other situations. So then to kind of informally justify to you why this argument is valid, why given these two situations, if P then Q, P, why Q must follow, let's look at this truth table and kind of analyze the situation. So for that, I'm going to break out my highlighter and I'm going to show you two things. First off, the premise is information we already know to be true. So my first statement, P implies Q, I know has to be true, which means I'm either in this situation, or this situation. So I can basically remove that whole middle portion because I know in this case that argument would have been false since the premise is given to be true and it's false in that situation. This can't be a situation I'm in. The second argument, which is just P, is true in my remaining cases only here, which means that these other situations where P is false here and here couldn't possibly be happening because again the premise of an argument are situations where this is known to be true. So that leaves me with only one situation, which is this first row, and in that first row the truth value of Q is true, which means that Q has to be true. That's why this is a valid conclusion. Now, the informal method lacks some of the details that we like to include in math to fully justify something. So let's look at a second way of justifying this argument, which is a formal verification. So it starts off very much like the truth table above. I'm given the same argument. I'm going to try to prove it more formally. I'm going to fill in my truth table with the values, similar to what I did above. And then I'm going to label a new column in this truth table, which represents the premise. Now the premise, again, is this situation here, which means that P implies true. P implies Q is true and P is true. And recall, we can represent that in logic by the little and notation. So I'm going to look at the truth values for P implies Q and P. That's my premise. So it'll be true, false, false, false. Because I'm again looking for when P and this is true. So it's true and true. Not the case here, not the case here, not the case here. Then I want to show that my conclusion must follow from this premise. Well, anytime something's following for something, it's basically saying that if this premise, then the conclusion. So I'm testing this statement. If the premise is my hypothesis, then the conclusion would follow. So let's see. Is it the case that this conclusion always follows from this premise? Well, using my broken promise rule to determine this, if this, then Q, yep, I have true implies true, so that'll be a true statement. And then recall that whenever I have an implication or a conditional statement, if the hypothesis is false, it's what's called vacuously true. So I don't even care what the values for Q are in this case. It's going to be true, true, true. So notice that for my test of the argument, all of my truth values in that test are true. That's what's called a tautology, which is always true. And I'll write that down here. Tautology. It's always true. Anytime you have a law of inference, every law of inference is a tautology. This conclusion will always follow from the premise, and it is always the case that that conclusion follows from the premise. No matter what the truth values of P and Q are, this conclusion always follows from this premise.
Impossible.
So this is the formal verification of any law of inference. Now there are several laws of inference that you should be familiar with, and here is the list of them. So we just verified law of detachment. We will verify a few others of these laws of inference in class, but what I want to do right now before the end of this video is just kind of go over what each of these is saying. Now the first one kind of makes sense, that if the statement Q always follows from P, then whenever P happens, Q should follow. It kind of makes logical sense. Similarly, we've already looked at in class that the contrapositive is logically equivalent to a given conditional. The law of contrapositive inference is kind of a combination of the first two laws. Since I know that given a conditional statement, such as P implies Q, its contrapositive would also be true. So I know that not Q implies not P. Given not Q happens, then I'm kind of detaching off that not P conclusion. So it's kind of a combination of the first two laws into one law. Law of syllogism, which we will usually never refer to as law of syllogism, we'll refer to it mainly as the chain rule, is another kind of simple statement. All it's saying is that if P implies Q, and then Q then implies R, I can simply say that P must imply R. So it's kind of combining these two implications into a single implication. Law of disjunctive inference, all it's basically saying is that given this disjunction, either P or Q happens. Well, if P doesn't happen, that means this is false. It must be the case that Q is true in order for this premise to be true. So that's what the disjunctive inference is saying. Law of simplification is saying, well, if P and Q are true, the only situation that occurs in is when both P and Q are true, then P by itself must be true. It's also true that Q could have been in this conclusion. So it's either of these are true as well. And then law of addition, if P is true, then I can add any other statement with an indeterminate truth value onto this disjunctive statement, because if once one of them is true,